Next, we'll look at complex analysis. Now, not everybody has had a full course in complex analysis, but most people have some familiarity. And the things that I'm going to talk about today are beautiful mathematics that really everybody should understand, that does mathematics should understand complex analysis at this level. So I'm not going to go slowly, I'm not going to go quickly, I'm just going to try to cover the concepts that are really important for analytic combinatorics. Complex analysis is really, for people with interest in computer science, it's the quintessential example of the power of abstraction. It's just an idea that we build on. Really, all of mathematics is like that, but complex analysis is really a perfect example. And the whole idea is that we've got -1. What happens if we want to take the square root of -1? No real number whose square is -1. So what we'll do is we'll define a number that's going to be the square root of -1, and we'll call that I. I squared is -1. Does I occur in the real world? Well, no, it's an abstraction. But it's an abstraction that helps us understand really a lot about the real world. So then what we're going to do, and all of these things are pretty simple, they get more complicated as we go on, but just starting with that idea, then we're going to want to do things with these numbers that involve this imaginary number I, like we're going to want to add them and multiply and divide them. We're going to want to do exponentiation. We're going to want to define functions. We're going to want to be able to differentiate them and integrate them. This leads to a whole theory that not only is beautiful in its own right, but also turns out to have many, many applications in science, in mathematics, and in particular analytic combinatorics. So there's many standard conventions, and again, I'm going to go quickly through these things, but many of them are elementary. It's really usually a matter of two things. One is the representation of complex numbers is by correspondence with points in the plane. So the point xy is going to represent the complex number z equals x plus iy. We refer to the real part of the complex number, r of z, and that's the x part. And we refer to the imaginary part, so that's the y part. Then the distance from the origin, so that's square root of x squared plus y squared. That's called the absolute value of the complex number. So how far it is from the origin is some sense how big it is. And then there's a thing called the conjugate. If you have x plus iy, then if that's z, then z bar is x minus iy. And so that's point flipped down on the plane. And I haven't defined multiplication yet, but when you do a quick exercise to show that z times z bar equals absolute value of z squared. So those are standard conventions for how we refer to complex numbers. Everyone's got a real part and imaginary part, and we represent them with points in the plane. Now, to define the basic operations, the natural approach is to just use algebra, but every time you see I squared, you just convert it to -1. So if you want to add two complex numbers, well, that's just algebra. Add the real parts, add the imaginary parts. If you want to multiply them, use the distributed law, I squared to -1, and then collect terms. So bd I squared, which is bi times di, becomes minus bd. That goes into the real part. And then bci and adi, those go to the imaginary part. So that's a definition of multiplication of two complex numbers. And this has all the right properties, it turns out, that you'd expect. Division, 1 over a plus bi, to make sense of that, multiply top and bottom by a minus bi. So then you have a minus bi over a squared plus b squared. That's the denominator is the number times its conjugate, which is the square of the absolute value. There's addition, multiplication, and division. And if you're not comfortable with those, you can try some examples with the points on the plane and so forth. What about something like exponentiation? Well, you can multiply a lot of times, but it gets complicated. So we'll skip right to one of the basic ideas of complex analysis. And that's the idea of an analytic function. So an analytic function is one that we can represent with a power series expansion. And we have the same concept in the reals with Taylor series and so forth. So we talk about omega being a region in the plane, and we talk about a function being defined in a region of the plane, and it's analytic at some point in that region. If for some little circle around that point, you can write a power series expansion of the function. And sure enough, this familiar power series from the reals are effective for familiar functions on the complex. So when z is a complex number, 1 over 1 minus z equals that power series where the products are defined as products of complex, and that's a valid series for as long as absolute z is less than 1. Or e to the z actually is valid except at infinity. Now it's a bit of a jump from defining multiplication to this, and I don't have the time to do the entire story leading up to this, but the main point is that our familiar series do translate through, and it's all through the concept of an analytic function. When I get in just a few minutes to some more concepts, I'll try to talk a little bit about why we know all this to be true. It's really part of a deep and beautiful theory that you need to take a course in complex analysis. For the purposes of this course, we're going to be using these kinds of series. And then there's the idea of complex differentiation. Well, we define that in the same way symbolically that we do for real numbers. So it's complex differentiable. A function is complex differentiable, or there's a special word called holomorphic. At a point, if this limit where f of z naught plus delta minus f of z naught divided by delta as delta goes to 0, if that limit exists for delta a complex number and z naught complex and f a complex function, so if that limit exists, it's holomorphic or complex differentiable. Now this is the same notation as for reals, but it's a much stronger statement because the value is independent of the way that delta approaches 0. It's a complex number. It can come in from any direction. It's a much, much stronger concept, complex differentiability. Now there's a basic equivalence theorem that says that a function is, that these concepts are the same. Analyticity and complex differentiability are the same concept. A function's analytic if and only if it's complex differentiable. We're not going to do a proof of that theorem. Really, for this lecture, we consider that to be an axiom. I'll talk about the proof in just a second. So if it's analytic, if you can express it as a power series, you can differentiate it. And of course, that's useful from the point of view of analysis, because it means that we can differentiate an analytic function term by term. If it's complex differentiable, it admits derivatives of any order, because you can always differentiate term by term. That's not really true in the reals. And in particular, we can use the Taylor series representations that I just talked about of familiar functions like e and 1 over 1 minus z and polynomials and so forth. So Taylor's theorem in terms of derivatives and so forth just immediately applies and gives us the power series that we're going to want. So that those are the kinds of power series that we're going to be extracting coefficients from in order to do our counting. There's a really famous particular example of this called Euler's formula. So that you take the definition of the exponential and evaluate at I theta. So what's e to the I theta? Well, it's 1 plus I theta over 1 factorial plus I theta squared over 2 factorial, and so forth. That's just right from the definition. Exponential is analytic. It's defined at any point, and so it's defined at I theta. Now, if you just convert I squared to minus 1 and I to the 4th to 1, then you can get rid of every other term has an I in it, every other term does not have an I in it, and then the terms alternate in sign. So I squared equals minus 1, so it's minus theta squared over 2. I fourth equals I squared squared equals plus 1, so it's plus theta the fourth over 4, and so forth. So that's just this is algebra, getting rid of the I squared. And then if you just separate the terms out from the previous slide, this first series is cosine theta, and the second series is I sine theta. That's called Euler's formula. E to the I theta equals cosine theta plus I sine theta. And this is an amazingly useful formula in many fields of mathematics. This quote from Feynman expresses what people think. He calls it our jewel, one of the most remarkable, almost astounding formulas in all of mathematics. And again, this is just an example of just starting with that idea of square root of minus 1. We can get to amazing constructs like this. That's what complex analysis is about. Now that's a very quick introduction. Next, we'll start to apply some of these things to the combinatorial problems that we've been working with. One thing that Euler's formula does is it gives us another way to find a correspondence between complex numbers and points in the plane. So e to the I theta equals cosine theta plus I sine theta, so r e to the I theta equals r cosine theta plus I r sine theta. And so we can use polar coordinates to refer to a point in the plane. If it's at angle theta and distance r, then we can write it as r e to the I theta. And we can, sometimes it's more convenient to use that form of the complex number. And we definitely often do so. So for any complex number, we can use these ways to convert between the polar coordinates and the Cartesian coordinates the same way as we do for points in the plane. That's an introduction to complex functions, and next we'll take a look at how to use this information to extract coefficients from combinatorial generating functions.